understand? That's the case. But in a situation where we have an isobaric system, or let's say an isochoric system. An isochoric system will be one that the work done becomes zero. But in an isochoric system, there is no volume expansion. Do you get that? There is no volume expansion. Do you get that now? So let's leave that with that. When we want to apply the concept of adiabatic processes or thermodynamics in equation, the overall equation you're going to be adding is the Q equals to internal energy plus W. This equation can be written like this: U equals to Q plus W. Different people have their different interpretations. It's not a matter of carrying over to another. It depends on how you view the signs. If this work is work done on the system, automatically it's going to increase the internal energy. So we're going to set it in such a way that it's going to cause an algebraic rise in the internal energy. And that's how the case is. So that's why it is most preferable. I advise my students to make sure the internal energy is outside, because it's more easier to quantify. It's just like saying if I increase Q and increase W, what's going to be the resultant effect? Or maybe the system, the surrounding thing work on the system. It simply means that there's going to be an increase in the amount of energy, in the system. Same thing with Q. If we increase the value of Q, that means we transfer heat into the system. It's going to also be an adiabatic and equivalent rise in internal energy. So you don't need to enter the other one and be worried about signing convention, or is it plus, is it minus, that's in the equation. The equation doesn't come that way. Although if they ask you for such, it is most preferable that you use U to be the dependent variable. Exactly. So that is that one for that one. Also in your thermal expansion, I can understand linear expansivity, volume expansivity, and superficial expansivity are common in expansivities. But we should also relate these things to what? To thermal stress. Now, the stress, thermal stress or strain. Let's use thermal strain. Thermal strain. If you subject or expose yourself to a strain, like maybe you subject the system to a strain, your body builds a coping mechanism, which is called stress, to be able to annul the effect of that strain. So in elasticity, it's easier to view the strain. Oh, I deformed this by extending this and all. But in temperature, if you heat up a metal, the metal increases in size, then it has expanded. And what genuinely makes it forward and expansion is the fact that it will contract after the whole expansion. Do you get that? So that's how the case is. Do you get that now? So that is for that. And if you look at the formulas of all your thermal expansivities, you see that we have T L1, L2 minus L1 over L1 change in theta. Right? Alpha. Delta is equal to A2 minus A1 over A1 change in theta. That's very good. Volume. So that's it. So that's it. We have V1. This thing that I'm seeing here, this change in V over V1 is called a strain. It's called a strain. And what kind of strain is it? Thermal strain. It's called the thermal strain. This is that now. So I told you, anything that brings about the strain must develop a coping mechanism for the strain to be evaded, right? So, in essence, even when we're using L, it's going to use V there. This one that we got here is called a bulk. It's called a bulk strain. Why? Because it has to do with the volume. You know, remember that bulk stress, shear stress. It's called a bulk stress. That's when you get from cubic expansion. But then when you're working from L2 minus L1 all over L1 change in theta, that gives you change in L over L1 change in theta. This one is called a linear stress. A linear strain, rather. But, and then, change. Linear strain, I don't understand. Strain is extension over original. You know, say that this linear is change in length expansion over the original. So, regardless of however you want to put it, this guy's thermal stress, thermal strain exists even inside thermodynamics. Then lastly, if you want to look at the concept of gaseous expansion, you will see that gases expand by themselves. Gases expand by themselves whenever they have been placed in certain kind of conditions. Just imagine, let me use the word, gases have the ability to do work on their surrounding spontaneously. How? You pump the balloon and it's moving on the road. Before you know it, it starts lessening by itself. That is compressional stress initiated by the balloon itself, by the gaseous system itself. Even when you heat gases, they expand, and they cause volume and continuous to also expand as well. It will create a stress on the walls. That stress is called a shear stress. A shear stress. So that's that for that. And from this. Is it a popular consciousness? Yes, but it's not a formula per se. So imagine this was a book. Imagine this was a book. And this thing came this way. And this way. What's going to happen? Like this can only happen only when you apply the force on an angle on the book. Because you see really straight now. At the moment, this edge is straight, right? The moment that I bend, I create a bend. This one is too high. If I create a bend like this, you know that kind of stuff that happens to the line of the whole book. Now, the deviation from here that you draw straight up, you will see that there's a part that came out from the original line. That part that came out is the stress, is the strain. The stress is still force over area. It's the strain that changes. Do you get it? So, I really want to appreciate us all for coming and being a part of this. Do take care and God bless you. Okay.
Open another go through here, so that you see the camera see.